Welcome everyone. Thanks to all for coming to our talk. In this presentation, we're going to talk about techniques to improve the text generation of an LLM. My name is Mikk. I've been a developer for more than a dozen years. I started by writing Objective-C, then Swift, but in recent years I focused on backend and Elixir. At the same time, along with the hype, I've been at times scared of, but mostly just interested in AI possibilities.
Hi, and my name is Milad. I'm a software engineer, and I've been working with Elixir past 8 years. I'm also co-organizer of Elixir Berlin Meetup, which we celebrated our 100th event last week. So if you are in town, second Thursday of the month, come and join us. We both are working in a company called High Mobility. We, as High Mobility, are providing a platform to access millions of cars on the road today. If this is interest of you, if it is of interest to you, just come and talk to us later. Few disclaimers. First of all, in the talk, just come and talk to us later. Yeah, amazing. Okay, so when we started or submitted our talk, we thought we can do all of this presentation in Livebook. Didn't work out with 2 people. So we will switch to the Livebook for the interaction part, and also we thought that we are be able to show you these techniques using Elixir LangChain. That also didn't work out, even though we are going to bring back some from our finding back and contribute back. And the last but not least is that we haven't applied this in a production. This is just the outcome of our research. With that out of the way, let's start. If you have been out of the loop, LLMs are very large deep learning modules that are pre-trained on a vast amount of data. They are making a significant stride on the tech community and beyond, under the point that you don't hear about Web3 anymore. In the opinion of the many experts, LLMs have a potential to become general-purpose technology, much like electricity and money and wheel. They can be used in a wide variety of applications. So if you use LLM without the techniques we are going to talk about today, you are able to use it to do text translation, text summarization, and so on. However, like many other general purpose technology, upon their introduction, they are faced public skepticism. Famously, when electricity was introduced, the first US president that had electricity in the White House, he hesitated to touch the key switches. And LLMs is not exceptions here, especially in their earliest stages. If you were here to ask you what are name few problems, I bet hallucination comes really on top of the list. And the reason is basically because LLMs are typing predictor on steroids. The way that it works is a company or a person collect vast amount of data, send it through a pipeline of complex pipeline training, and then an LLM is born. The response that you get from an LLM depends on A, amount of data we use, and B, also the time that the data were collected, because it cannot answer about the facts or event that happens afterwards. And that's the myth of our talks. How can we address that? I'll hand it over to Mikk to explain it to you.
So I'll start by quickly going over an AI project's lifecycle. Every project begins, obviously, by defining the use case or scope of the project. After the requirements are locked, we need to choose our model. We can either train a new model. This could take a lot of resources to produce a well-working one, or we can use an existing model to adapt to our use case. After we have zeroed in on a model we like, we can further refine it. To do this, we have multiple tools to choose from. We can engineer the prompt in a way that consistently produces the output we want. This is easy to play around with, but could be hard to get just right. If we earlier chose an existing model, we might fine-tune it to shape it more to our use case. This requires some deeper knowledge about machine learning, but there are great tools available, and we've seen some already today. If our use case or task is hard to define, but easy to judge, we might consider alignment with human feedback. It's used when humans easily understand what the target goal is, but it's hard to define and write down. For that, humans would rank the output of our model, and that would be used to train another model, which would be used to improve the output of our main model. Whatever tools we use, we always keep evaluating and testing the model to see how it performs. Once we're happy, we can move on to the last phase of integration and augmentation. Here we might try to optimize the model speed and some other performance characteristics. We also need to find the hardware we're going to use for inference. Usually it's going to be some big cloud provider, but of course one can run the inference on local chips as well. Finally, we'll get to augmenting the model and the approach we're showing in this talk. It's a technique called RAG. It stands for Retrieval Augmented Generation. It's a term coined in a 2020 paper presenting a technique that enhances the model's ability to provide accurate and detailed answers by leveraging both the knowledge encoded in its parameters and specific information from external sources. This means we could make the LLM smarter by providing the model with an improved context, and it would, based on more information, be able to give better answers. Meaning, we could feed the model with new data it never saw during the training, or it was too niche to generalize for. We could keep the generation up to date even after the training is finished, saving us from having to rerun the costly training process again and again. Finally, we could also use private data to improve the generation. If you used an existing model, creators of that likely or hopefully never had access to our private data. Or it could be some sensitive business-critical data that we didn't want to lock into our model. Even more, we could keep the model smaller and faster as it doesn't need to store or learn all the retrievable data. Unlocking these benefits is as easy as following 3 simple steps. First, we need to prepare our system by indexing and storing the data. As a simple approach, we could use an SQL database to store our structured data in. Next, when a user asks a question, we try to retrieve data related to the question and add that as extra context to the query. And finally, we use the LLM to generate the more informed answer back to the user. However, using this naive SQL approach has some drawbacks. Simple search from the database lacks the semantics to confidently find related data. We can boost our confidence in finding related data using vector embeddings. It's an old idea from the 50s and 60s that has resurfaced thanks to the AI boom and especially the drastically lower costs of inference. Vector embedding uses ML models to semantically capture the data and convert it to vectors, allowing us to search through them by their semantic similarity or meaning. In other words, it translates high-dimensional information like words or phrases into vectors of fixed, lower dimensions in a way that preserves the semantic relationship between them. Meaning, similar words are mapped to points close to each other in the vector space. The magic of these embeddings is that they capture the essence or meaning of the items in a way that maintains relationships. Similar items end up close together in this space. Now, let's jump into Livebook to see how these vectors look like and how are they similar. So we set up our dependencies and the NX backend. So for creating vector embeddings, we've chosen a small model from Hugging Face. It only has 22 million parameters, but that's good enough and mainly fast enough for this live demo. We'll create vectors for 3 random words. And as we look at them, we can see that they are a list of floating point numbers. The lists are 384 dimensions long. That's because of the embedding model we use. Now let's see how similar these vectors are to each other. We're going to use cosine similarity because in text analysis, directionality matters more than the magnitude.
Could you zoom in? They ask.
So, in other words, we're going to see if a dog vector and a cat vector point in similar directions. So let's have a look. So in the bottom, we can see that dog and cat vectors are fairly similar, but airplane is quite dissimilar to either of the pets. So let's try some different inputs, but do it in a fancier way with Kino. So here we're gonna see if author of tune, how similar it is to either of the two texts. So as you can see, the second text has quite a high similarity score, which confidently tells us that these two, the input and text 2, they have a similar meaning. Also, the first text has quite a high score as well. It may be because the embedding model has some encoded knowledge about tune. So if we instead check for author of foundation, we can see that the text and the similarity scores are quite low. So, yeah. So back to the slides. So being able to search by the similarity or meaning gives us an opportunity to effectively use vector embeddings in areas like natural language search. So think of Google or any other search engine, or a powerful recommendation system, something like Amazon or Netflix, or documentation and customer support. So think of a chatbot for any company. Not covered in this talk, but images can also be vectorized by semantics. Just imagine different layers in a ML model detecting ages, shapes, and further abstract concepts. And there are certainly many more that we can think of. So all this was possible to do before the AI boom of recent years, but was mostly restricted to big companies like Google or Amazon. Next, Milad will tell us how to use RAG with vector embedding.
Thanks. So let's, with this knowledge, update the graph that we saw before. So we have our application, get the data, give it to the embedding model, get the vectors back, and then store it into a storage system. When the user asks for the query, we retrieve the similar contents and then ask LLM to answer that, and then we get the answers back. But the algorithm that Mikk showed was a cosine similarity, has some. It's good for showing off the difference between the words, but then it doesn't work in the higher scale. You need an efficient way to search through all of your data. There are two kinds of algorithms to do this kind of lookup. One of them is KNN, which is basically you pick one word, you pick one vector, and then try to find the similar in all of your data set. The other one is called ANN, or approximate nearest neighbor. The idea is that it's an algorithm that can locate the nearby vectors. There are many implementations of ANN out there. There is one FICE by Facebook, HNSW. There is an Elixir library for that, and also Annoy by Spotify. I'm going to tell you how Annoy works. It's quite interesting if you don't know about it. So imagine that we spread our data points in a 2D space like this. And before doing any search or lookup, we try to divide the area in our data set. First, we pick two numbers, random numbers. I conveniently chose 1 and 8. And then draw a line between these two locations that have the same distance from these 2 points. And then you keep doing this repeatedly until the area that you have has 3 or 2 items in it. Why 3 is just an arbitrary number I picked for this explanation. We do the same thing to the right, and now we have our binary tree. We are able to do search using a binary search with which, as you know, has a big O notion of like n. So it's quite faster to do lookups. Now, if I want to find the location, find the nearest points to this cross line, all I need to do is I say, is it close to 1 or 8? It's close to 1. So we take to the left side, and then we do the same. It's close to 7, and now we got the nearest neighbor. If you probably ask, what if the cross was a bit to the right, and then we would have find 5, 12, and 4? You're right. However, the promise of ANN is that given that you have massive amount of data, it's much faster to do lookup, and at the end you will get a really pretty good results with some level of mistakes. Now I just shared this one just to give you an idea how does it work, but in practice we are not going to use this, at least in this talk. We are going to use vector databases. So the idea of the vector database is basically they are optimized for doing store, index, and query vector data. There are a lot of databases are supporting this. New ones are popping up every few months, and as you see, there are some familiar faces here too. It turns out that the old databases can also handle this kind of vector data. We use Postgres with the PG vector extension. The reason is that, especially in Elixir, it's much easier to use existing connection. There is a client for that. And if you decide to use PG vector, make sure to read the documentation. The way that the querying and the indexing works is quite different. You need to make some decision making in advance. And I will show you how does it work quickly. I hope it's picking up. So you can run PG vector using Docker simply by running this command. There is some set configuration that we need to do to configure the PG vector extension, and then our repo is ready. Before you use vectors in any database, you need to create an extension of vector. And here now we have a migration that we say we want to have a column called embedding with the type vector, and the size is 384. If you remember, the model that we are using for embedding is 384, so you need to make that decision up front, which model you want to use. I already ran the migration, so I don't do it here. And so now let's say that I already converted 2 words, cat and dog, and got the embedding. I'm going to insert into database. So the first record is the cat, and then the second record is dog. And here I have a query that again created embedding before, vector embedding. And it says that when I was a child, I had a cat. And this is how you can query it. Basically, normal ecto. It's just that the query has to go to the order by, and this is my original query, and it should return the first row as a match data. Okay. So let's put everything that we learned together. We want to make an application that scrape hex documents, convert it to the vectors, and then store vectors in the Postgres, retrieve the similar context, and ask GPT, OpenAI API to answer the question. Okay. So we have this database which we went through already. The only difference is now I keep the text because I want to feed it to an LLM as a context, and also I keep URL because I want to ask for the URL. And next we have the ecto schema. We are setting up our embedding model to get the vector embeddings. Here I'm trying to fetch some contents from the hex and then try to create the embedding of them and store it in the docs, which I already did to speed up the talk, and insert into the database. So in order to ask an LLM to give you answer, you need to work on the prompt engineering that we mentioned before. You need to work on it. So here it says that you are advanced virtual assistants, that this is the source and context of the data that we provide to you. please answer the question. And we are talking about this is Elixir, this is your handling hex document, so it's important to give also right context what it's supposed to do. I also tried to few times mention don't hallucinate and so on, but I hope that works. Let's start running the query. We want to ask GPT without any RAG. We want to, what I have here is just an input box that called inference function without any context. So we are asking how to deploy Livebook. Let's see if the god of OpenAI is not happy. Okay, second. If it didn't work third times. Yep. So we wait a lot to get garbage back because Livebook it's not possible to install Livebook like this. I mean, you could potentially, but it's an app, so probably that's not what you want to you ask for on the LLM. And it says mixed Livebook server, no. So, but now let's switch to the option with RAG. What we are here doing is basically when we get the input, we give it to the embedding module, get the vectors, and query the database, put it as a context, and now we have the context. Let's ask how to deploy Livebook. Did I push it? Okay. This is a pretty accurate, I guess, answer. All looks familiar. I was deploying Livebook a few days ago. So as you see here, we got much better answer. I can also ask something that's not related to the Elixir, like, and then you see that because of prompt engineering, we said that if this is not Elixir, don't answer. It will refuse to answer. We will skip that part. So this could have been the end of our talk, but unfortunately, there are more as usual. I give it back to Mikk to explain them.
So, as powerful as all of this already is, as Milad mentioned, there are some issues that will degrade the performance of our system. One obvious problem is context size. It defines the amount of data the model can work with. Embedding models used to vectorize data often have smaller context sizes, which leads to information loss for longer documents or complex input. LLMs, on the other hand, can handle noticeably longer contexts, but have their upper limits as well and can't fit everything vaguely related to the query. Furthermore, giving the LLM too much unrelated data can bury or obscure the actually useful data we had related to the query. Usually, we need to limit the input and thus have an adverse effect on the generation. These limitations push us to split the data into chunks. So chunking is a technique to split our data into smaller, meaningful pieces to fit our context limits and help us retrieve more relevant information. For that, we need to consider a few things. Optimal chunk size is important for balancing semantic capture and compute efficiency. Larger chunks would offer more context, but at a loss of finer detail. There is also the danger of splitting across critical sections, thereby losing the original meaning in the data. Just splitting by fixed number of characters is prone to fragment our data and produce a subpar result. Instead, we could cut by sentences, paragraphs, or even documents. Or we can use more advanced techniques like splitting semantically using other ML models. To mitigate some of these issues, we could use overlapping to improve context retention. We can overlap, for example, by a number of characters, sentences, or sections. Another problem we might face is how to deal with different types of data. Documentation written in Markdown has a different structure to a YAML one. Regardless, whatever choices we make with chunking, our main concern is context fragmentation, the risk of losing the meaning in our data. After considering chunking, there are some other hurdles we'll likely face. Among them are scalability issues. The sheer volume of data needed for effective retrieval can balloon. As our dataset grows, so does the complexity and resource requirement for indexing and retrieval. Distractors. Retrieval mechanisms might fetch irrelevant or misleading information, especially if the query is ambiguous or the indexing isn't great. Imagine asking for help with Elixir and getting a potion receipt. Not really helpful, and it can mess up our entire generation process. Language and domain specificity. Embeddings trained on general datasets might struggle with niche or technical domains, like mistaking a coding language for a spoken one. On ways to improve our current approach, I'll hand it back to Milad.
Thanks. So, as I mentioned, if you want to change your retrieval system in a RAG using similar contents, it's possible that you try to fetch something that doesn't exist in your database and eventually return it back to you. So, and also, the other problem is that user can ask ambiguous question, and ambiguous question gets ambiguous answer and hallucinations. User can ask what kind of transformation can be achieved with Elixir. So if it's somebody asks you this question, you will probably ask, what do you mean? What's the context? Could you give me more information? We can do this with LLM. The first approach is called multi-query or query expansion. The idea is that when somebody gives you a query, a user gives you a prompt, you give it to LLM and ask LLM to provide more context to this question, maybe add some more question related to this. And then you use the expanded queries to go for your database and find the similar contents, and then pick the top 3, for example, and give it to LLM and get the answer. I try to, okay, I guess we are a bit short of time. We don't do the demos, but if you scan the QR code, you will end up to the same Livebook, and you are able to play around yourself. I guess that would be much more interesting for you. But basically what it does is just additionally tries to make ask a question from LLM and include it in the context and in the retrieval. There is another approach called PG RAG fusion, and it's your cross-encoder re-ranking. The idea is basically the same, but when you get the data instead of 3 in the previous example, you get more data, and then you give it to another machine learning model to rank those answers for you, and then you pick the top 3 again and give it to LLM and get the answer. This is how the cross-encoder ranking works. Is basically gets the data, gets the original query and what you retrieve, and you can see how related is it. You might ask that if we already had the vector embedding, why do we need to do that? I should remind you that when we did similarity search, it was based on the vector, not based on the text. It was just representation of vector. But in the cross-encoder, maybe it can emphasize different part of similarity between 2 texts. It's always good to test different models and see what fits your use case. We work on some demo application that does a lot of techniques that we talk, especially chunking and also query translation as we discussed today, so you can play around with that there as well. And we also want to, if you want to continue learning more, I suggest you to look at these 2 contexts. One of them is RAG from scratch by Python LangChain community. It just dropped a few months ago or 2 months ago. And also deep learning.ai has lots of good courses, including this one that we use in our talk. Thank you.